Good morning, guys. This morning we're going to finish our lecture about architecting and design software. Last time we discussed about what is design and what are the design principles that lead to having high quality software. Today we're going to start talking about software architecture, okay, which is the first step to take towards designing a good high quality software. So first of all, what is an architecture? So usually when you build buildings, architecture is the first thing that you design, because this plays a central role in the entire construction. So usually the architecture represents all the aspects needed to build a building. The electricity, plumbing, structures, how many floors, stairs, elevators, and so on and so forth. Okay, so well, software architecture is essentially the same. So we want to mimic the same process, but talking about software, of course. And then the software architecture just design the organization of the software system. Okay, what does it mean, organization? Well, it means the different subsystems. So last lecture we discussed, introduced this divide and conquer methods. So starting from the big problem, we want to divide the big problem in small problems and then solve these sub-problems into isolation, and then finally recompose all the different solutions that we have found during the design process in order to solve the big problem. Okay, well, subsystems identifies the small problems. Okay, we want to build up really large and complex system. Dealing with this as a whole is very difficult. Then the first step would be to start dividing the system in different subsystems, and then work on in the subsystems in isolation. Well, the aim of the software architecture is exactly this one. So allow us to divide the system in subsystems and organize the different subsystems. But once we have this subsystem, then we have to decide and design how this subsystem interact each other. Okay, so the subsystem exist in isolation, but they have dependencies. Okay, they must interact each other. For example, for sending, sharing information, or using different functionalities. And then we also need to define how this interaction takes place. And then this should be through the well-defined interface. We also discussed last lecture that information hiding is a key concept for having a good design. And then all the interactions between subsystems should take place through interfaces. Okay, never access internal attributes or internal data or internal mechanisms provided by the subsystem. We always have to interact to the subsystem by using the set of interfaces that they provide. Okay, then so the software architecture allows us to accomplish these three tasks that are very important for designing high quality software. Well, for designing any software, but if we want to achieve design, this is much more important. So the architecture is really the core of the design. Okay, it's the first activity that we have to perform because allow us to organize the system into subsystem and to assign responsibilities to different subsystems. So the idea is that in the real world, once you have subsystems, then you can assign a given subsystem to a specific development team, for example. Okay, and then this development team can solve and implement the subsystem in isolation. And also the architecture put constraints all over overall the efficiency, reusability, and maintainability of the system. If we architect the system in a good way, then all these properties comes for, well, not for free, but comes from by definition. Okay. So let's start with this divide conquer. What is a system? So the system is a logical entity that have some responsibilities or objectives, okay, and can be hardware or can be software or both, okay. So it can be a robotic arm that works in a factory, can be a piece of software managing the users, for example, or can be, well, software that manage the hardware. Then as the goal so the responsibilities for this system must be defined according to the requirements. Okay, so the requirements is always our starting point. Okay, remember the requirements define the big problem. Then our aim is to solve the problem defined by the requirements. Then the different subsystem should take in charge the requirements. Okay. Then the responsibilities for the system should be elicited from the set of requirements that we defined in the requirement analysis. Of a system, as we said, can and should be implemented as a collection of subsystems. Okay, still the idea of the divide the requirements in the set. In different sets of the requirements, and then assign a subsystem to each set of requirements. But what is a subsystem? A subsystem is yet another system. Okay, this is towards the definition of we want to make a system made of systems. Okay, then a subsystem is still a system that can live in isolation, can work in isolation, but interacts with the other subsystems. And all this interaction, as we already said, takes place through the well-defined interface. That's even also a very important thing. And then we have modules. Okay, modules are defined at the programming language level. Can be classes, can be methods, can be packages. Okay, if we are discussing about Java, many modules can make subsystems. Okay, and many subsystems can make one system. That's the hierarchical organization of a given system. So, how to implement an architecture? We need this architecture because we want to understand the system, okay? And then if we are able to split the big system into subsystem, it's much easier to understand, okay? So if you think about I don't know, university management. Okay, then you have one subsystem dealing with the students, one subsystem dealing with the staff, another subsystem dealing with the students' enrollment in the courses, one subsystem for paying your roles, and so on and so forth. Okay, so depending on the specific goal, we might create a different subsystem, and then we can understand how the big system work together. Allow people to work on subsystems. As said, we can assign subsystem to a specific development team. So a development team can deal with one specific subsystem in isolation without knowing what's happening in the other subsystem. The only things that they need to know in order to interact with the others is the interface, okay, which is provided by the other subsystem. You don't need to understand and know all the details within the different subsystem. Allows us to prepare for extension of the system. Remember last time we talked about having some hooks, okay, within the implementation that allows us to plug in new functionalities if we want to extend the system. Well, this is done by means of the software architectures. Okay, if we define a software architecture properly, then it will be much more easy to extend this the software. Okay, by including a new subsystem, for example, or including new modules, or replacing a specific subsystem with another subsystem that implement the same interface, so that you don't break the dependencies with the other subsystems. And this also facilitates the reuse and reusability, because you can make one subsystem into isolation, and then you can reuse this subsystem as a whole in another project. So usually a software architecture is expressed and represented in terms of different views. So as we said, when you have an architecture for a building, then you have plumbing, you have electrical stuff, and then you have the floors, and so on and so forth. Okay, they are different views of the same building. Then we want to have the same thing for architecture. Different views representing different aspects of the software architecture. So the logical breakdown into subsystem that is known as components. So sometimes we use components for saying subsystem. Okay, then it's a synonym. And then all the interfaces among the components. This is usually expressed by means of a UML package diagram and the UML component diagrams. Okay, then we will use these two type of diagrams for depicting how the different subsystems will interact each other. Then we need to define how these components or subsystems interact each other at the runtime. Okay, and this is done by means of UML sequence diagrams and UML activity diagrams. Okay, then by using these different diagrams, you can define how one specific component will interact with other components. Okay, then the temporal exchange of messages between the two. So, and how the activities, for example, involved in a workflow are accomplished among the different subsystems. Then we're going to use data class diagram for still UML class diagram for representing the data which is shared among the different subsystems. Okay, for example, you have to send information about a user from one subsystem to another subsystem. Then you can define this user data by means of a class where you can put all the different attributes, okay, included in the data definition. And finally, the deployment. Okay, we need to express how we deploy our software system on the real devices. And this is done by means of UML deployment diagram. Okay, then you can define how these components are deployed in real devices. Okay, then for example you can have one component deployed on your desktop machine, another component deployed on the cloud for something, for example, and so on and so forth. Okay, then we don't go. So are you familiar with these diagrams? I guess so. Okay, then this is something that I give for as assumption. Then we don't need to explain how they are used. But so just remember that we want to use these different diagrams to express the different views that we need to define the architecture. Then first, the different components and their interfaces. Then how these components interact each other, what type of data they exchange, and how we deploy these components on the set of devices needed for running the software. So, but let's see how to develop an architectural model. Yeah.
So, what's the difference between architecture and design? Lots of these activities are similar to design.
But architecture is design. So the architecture is the first level of design. Okay. Then you first design the architecture in terms of subsystems, components, interfaces, and so on and so forth. And then you can design every single subsystem. Okay, for example, by means of design patterns and so on and so forth. Okay, then so it's still design, but it's the first level. It's the highest level. Then let's start. How to develop an architectural model. So how to define the architecture of our software. First, start by sketching an outline of the architecture. Okay. So for example, try to map the requirements and the use cases on subsystems. Okay. If you have, I mean, usually when you have the requirements, you have a list of functionalities. Okay, try to group together functionalities that are related to each other because of the cohesion design principles, okay? And then try to assign these requirements to a given subsystem. For example, if you want to manage the students in the university, and then you have to put all the functionalities related to the student in the student management subsystem, for example. Okay, don't mess up functionalities related to the students with functionality related for the paying fee payments, for example. Okay, fee payments. Okay. The fee is paid by the students, but this functionality should be provided by the completely different system, which is the subsystem that deals with payments. Okay. Then try, so once you are able to map these functional requirements and the use cases to given subsystem, then try to determine what are these main components. Okay, then if you have a group of functionalities related to the user's management, then you can say, okay, now I need one component or one subsystem dealing and providing all these functionalities. Okay, and then choose among the different architectural patterns that we're going to discuss soon, in order to understand how to organize the different components, okay, together. So once you have this first high-level sketch of the architecture, then you can refine it. What does it mean, refine it? Try to identify how these components should interact each other, okay, and what are the different interfaces between them. Okay, so the interface is essentially define the set of functionalities provided by each component or each subsystem. And then define how the data and the functionality are distributed among the different components. Then try and consider the use cases, okay, and try to adjust the architecture to make it realizable. So usually it is an iterative process. Okay, it's very difficult that you start with the initial sketch and this it's perfect. Okay, then try to make the sketch and then try to run the different use cases on the first sketch. And if it doesn't work, try to adjust all the different components and functionality. Sometimes you discover that it's better to split one subsystem into different subsystems, okay? Because this will help the use cases and so on and so forth. So once you're happy, then you can mature the architecture, okay? And then you define the final set of components, and well, still by means of the component diagrams, and you can highlight and define the exact sequence of interactions, okay, between the different components, still by means of sequence diagram. Okay. Always use these diagrams in order to highlight this stuff. So then we mentioned about architectural pattern. What are architectural pattern? So usually pattern, yep.
Just on the previous slide. So we can use sequence diagrams in different levels than we can use for, like on the high level, when you have the communication between the different components.
Mm-hmm.
Then you can use also for example, to specify one method and then this method.
Yeah, exactly.
But in this level is on between the components.
It's in between the components. So usually sequence diagram has been invented for depicting the interaction between the classes, right? That are really low level. But we can reuse the same sequence diagram for depicting and defining the interaction among components, okay, that are more high-level entities. Okay, sequence diagram are the same, so the rules governing how to make a sequence diagram are exactly the same. What's changed is the level of abstraction. Okay, instead of classes, we talk about components. To some extent, also a class can be a component. I mean, you can implement a component by means of one class. Then in that case, the two abstractions collide, okay, coincide. But that's not the usual case. Usually, a component is made by a set of classes. Then if we talk about in terms of Java programming, then a package, okay, can be seen as a component, logically. Okay, no, I mean, if we stick to exact definition of component, the components are a bit more. But as a rough idea, you can compare a component with a package in Java.
Because at this stage, we don't know exactly how the classes will be implemented or anything, but we just have a rough idea on how they should communicate with each other.
Exactly.
Okay.
So, for example, I forgot the marker. Okay, here we have some marker. For example, if we want to implement for example, a usual e-commerce application, okay? Then you might have different requirements. for example, adding the items to the cart, okay? Well, browsing the store, then putting items into the cart, and then check out the cart, pay, and then there is the delivery of what you bought to home. Okay, the different requirements. Then you start grouping requirements together, and then you might say, okay, this application can be divided in different subsystems. Then I can have a first subsystem about items. Okay, I can browse the items, and then I can choose the items that I want to buy, and so on and so forth. Then you might have a subsystem which is the cart. Okay, where you can add items to the cart and then check out the cart. Okay, then this means that these are two different subsystems. They might interact each other. And then you need something for paying. And then you might identify another subsystem for payments. And then you have shipment. Okay, that's the first sketch of the architecture can be this one. Okay, 4 different subsystems. They can be implemented in isolation by different teams. And then they deal with 4 different aspects of the entire software that we want to develop. And then you start thinking about, okay, these are the items, so the items might need a database, for example, where we store the items. Then the second step is to add a new subsystem for the data. Okay. And then you start highlighting the different interfaces. For example, the items need to interact with the cart because you want to put some data into the cart, for example. And then for checkout the cart, you might need some payments, and then you want to ship, and then you need, well, that's just an example. Okay, and then you start trying to run the use cases, okay, highlighted and defined during the requirements. And then you can notice that something can be missed, or something is redundant, or this initial architecture is not very good. Then you need to refine. For example, as in case we need database, and so on and so forth. Okay, that's it's an iterative approach, and as we said last lecture, so design is also a creative process. Okay, then you need to use all your knowledge and the knowledge that you acquired by books or by the best practices and so on and so forth. But it's also a creative process. Then, yeah, you need to invent solutions. Then architectural pattern. This is very important thing. It's something that will help a lot. For example, in this case, if we use an architectural pattern, this architecture will be much more easy and much more good, okay, well established. So then what is a design architectural pattern? So the idea is to exploit so the same idea of design patterns. Okay, so a pattern is usually a reusable solution to a general problem. Okay, that you or someone else encountered in the past and in particular context. So you know about design patterns, right? Then you know that whenever you face a specific problem, you get your collection of design patterns, and then just pick the design pattern that best fit your problem and then apply it. Then you can apply it because you know that it works, because it's been proved, because it's part of the best practices in programming. Okay, then we want to exploit the same idea, but at the architectural level. Okay, not yet talking about the code. So let's see if then, so yeah, as said, we want to apply the notion of patterns to the software architecture. They are called either architectural patterns or architectural styles. Okay, if you search around, you found these two terms for indicating the same thing. There are many different type of architectural pattern. All of them makes use of components. Okay, so the components or subsystems is the building block here. Okay, then we use components, and we use components because they are independent. Okay, usually a component is a piece of software which is completely independent on the others. I mean, you can have dependency. Okay, I mean, for example, in order to here the cart, what the items here has some dependencies with the cart because you use some functionalities provided by the cart, but it's independent because you can deploy it in isolation. You don't need to compile all together. Okay, you compile only the item subsystem, okay, in isolation because this has been developed by a given team, and then they develop this subsystem, test the subsystem in isolation, and then they can deploy this subsystem in isolation. And then at runtime, it will use some functionalities from the cart, but at runtime, not at compile time, as you do with classes. I mean, when you have dependencies between classes, these dependencies must be solved at compile time. Otherwise, the compiler is not able to compile the entire program. Okay, that's not the case for components. So this should be compiled and deployed in isolation. Okay, then it might not work because I mean he might need something from other functionalities from other subsystem, but well, it's still alive and running. Then there are many different type of architectural pattern. Let's discuss some of the most used and most useful, okay, design patterns. So the easiest one, and I think one of the most used one, is the multi-layer architectural pattern. The idea is to split the system into subsystems. Each subsystem should be seen as a layer. These layers have a well-defined interface, okay, which is the API. And the idea is that so layers are superposed one each other. Like, do we have something for raising? But I have a picture on the next slide. Something like that. Okay. Okay. Each layer can access and interact only with the layer below. And this allows us to increase the level of the abstractions. I mean, usually the bottom layer provides very low-level functionalities that are used by the upper layer to build more complex functionalities that are used from the upper layer to create much more complex functionalities. Okay? So usually the bottom layers provide general services, for example, network communication, database access, and so on and so forth. Okay? In fact, this is the usual three-tier architecture, where you have DB, database here at the bottom layer. Then the application function are what this implements the business logic. Okay, hold the set of functionalities that are specifically related to the application that you are building. Okay, and usually is the middle tier. Okay, called business. In our previous example, here you should have browsing the items, add the items to the cart, pay and ship, and so on and so forth. Okay, all in this layer. And then finally, the uppest layer usually provides the user interface. Okay, then the user interface make use of business logic. Okay, in order to allow the user to use the functionalities of the application, and the business logic use the database, the data management layer to store the different data. Well, this is of course, I mean, this is a three-tier, but you can have as many layers as you want. The important things is that so bottom layers provide an interface which is exploited by the layer above, then provide a new interface which is exploited by the layer above, and so on and so forth. Usually the first layer do not use anything, and the last, the upper layer does not provide anything. That's why you usually have the user interface here, okay? Because above the user interface there is the human. Okay, you don't provide any API. Okay. And in fact, this is the usual typical layers in an application program. As we just discussed here, you have the user interface on the top, application logic in the middle, and then many low-level layers at the bottom. We have one layer for the operating system access. For example, I don't know if you have to browse the file system or you have to print out a document, and so on and so forth. Then you have database access and network communication. Here, I mean, I just depict one layer, but you might have many different layers at the same level, okay, providing different functionalities. This is very good architectural pattern because it provides a lot of things with respect to design principle. Allow to divide and conquer the application, because every single layer can be designed independently of the others. Okay, then you can split your application, for example, in 3 different layers, as it is here, and then you can assign the different layers to specific development teams. One team will deal with the user interface, one team can deal with the application logic, one team can deal with the database. Okay, then you can divide the big problem to provide a software for e-commerce in 3 different sub-problems, okay? And then in 3 different subsystems and deal with them in isolation. Provide a lot of cohesion, because every single layer should provide a consistent set of methods, okay, of functionalities. Okay, as we seen here, for example, we have three different layers in the same level. One providing all the functionalities dealing with the operating system, one providing all the functionalities dealing with database, and one dealing with all the functionality provide the network communication. Okay, that's cohesion, very important. This group together all the functionalities that are related to each other. Coupling. Well-designed low relays do not know nothing about the higher level layers. Okay, the only connection between the different layers is through the different interfaces, then the API. Okay, then this layer does not anything about this layer or any internal mechanism on how they deal how they deal with the data. It doesn't know if data here is kept by means of XML files, JSON files, or NoSQL database management system, or SQL database management system. I mean, that's something which is internal to this layer. Okay, the business logic should be completely agnostic about how the database management system is implemented internally. Okay, you just use the interface here provided by this level. Abstraction, I said, you don't need to know the details. Okay, about every single layer is implemented. Reusability, because I mean, once you have this layer or this layer, you can reuse the layer in isolation in other different project. Okay, and then of course reuse. If you have as you increase the reusability, you also increase the reuse of the given level. That's it. Okay, these are the different design principles provided by this type of architectural pattern. Then another very important and used architectural pattern is the client server. Okay, we are quite used to use this to exploit this. This architectural pattern. This is the architectural pattern that we exploit every day when we navigate the internet. Okay, the client side is our browser, and the server side is the website, web server we connect. Usually, so at the architectural level, talking about in terms of components. The server component is the component that provides all the functionalities, okay? And the client, as you can see, just interact with the server and consuming the different functionalities provided by the server. The server is alive and waiting for connection. And then usually it's the client that initiate the interaction with the server. Okay, you need the web page. The server is there. Doesn't matter if there are clients connected to the server or not. Okay, the server is awaiting for a connection. Then when you need a web page, you start up your client, which is your browser, and then you issue a GET. Okay. Message to the server compute the GET, HTTP GET, and then answer with the content that you want to display. That's it. This client-server architecture can be further extended into a peer-to-peer system. You might have used a peer-to-peer system to download movies or music from internet. Good examples are BitTorrent, and then there are many others. For example, one of the first was Napster, okay, but there are Heymule, and so on and so forth. Many different peer-to-peer systems. The idea here is that every single component is both a client and a server. Okay, that in fact I mean, as you see here, we don't have this lollipop symbol because every single component provides the same set of functionality, okay, to the other components, and use that functionality is provided by another component. Okay, they exchange messages. For example, you can download a movie from a client 3. From I mean, client 1 can download the movie from client 3, but also from client 2, and client 2 can download from client 1, and so on and so forth. All of them provide the same set of functionalities, and all the others make use of this functionality. This is a pure peer-to-peer pattern, but usually we don't have any pure peer-to-peer pattern. In practice, what we have is usually a mixed peer-to-peer and client-server system, because we always need a server here, okay, where clients can connect to the server and then discover the other clients, okay, to connect with. That's why, for example, when you want to use a BitTorrent, you first search on the web server for the key of the magnets, links, whatever they are called, in order to download. This provides you the internet addresses of the other clients. Then you are allowed to connect directly to them. Okay, that's a lookup address operation provided by the server. This is also very nice, well, both client-server and peer-to-peer are very nice architectural patterns. They also provide a lot of good design principles, allows you to divide and conquer, okay, because every single, well, clients or servers or in the peer-to-peer, they can be developed in isolation, okay, then separately. Allows you to increase the cohesion because the server provides all the services, okay, all the functionalities. Then you have a separation of concerns between client and server, and then increase the cohesion. Coupling, there is always one communication channel, okay, between the client and the server, and then you exchange messages. Okay, and this decouple the two, because I mean the server is completely agnostic about the clients. So you might have only one client, but you might have a million or billions of clients. Okay, for example, as it happened on the internet. I mean, when you deploy your web server, you don't care about the clients. Okay, you never know if you will have one client or 1 million clients, or if the clients will run on a Windows machine of Mac OS or iOS or whatever. Okay, there's no completely low coupling in this sense. You only have the communication channel, okay, and then you exchange messages on this communication channel, which is managed at the network level. Increased abstraction because separate the distributed components. Okay, then you always have a clear distinction and abstraction between the client and the server in this specific case. Increase the reuse. It's very easy to find out suitable frameworks, okay, on which you can build a good distributed system. I mean, you don't have to reinvent the wheel every time, okay? In the client-server application that we just discussed, you don't have, for example, to implement the network. You can just use a framework that implements the communication channel, for example, to increase the reuse of the system. Sometimes happen that these client-server system are very specific with respect to the application that you are building. Okay, that's in case, for example, you don't use or you define your own communication protocol. I mean, if we use the example of the web application, so the communication protocol is HTTP in that case, which is a standard, then it's okay. But you can create your own protocol, okay, that let a client to communicate with the server. In that case, so reusability is not very good. I mean, you cannot reuse it easily because of this protocol. But using the frameworks, for example, the HTTP frameworks, will increase the reuse of the system. So another interesting architectural pattern is the pipe and filter, but we're going to discuss it after a short break. Okay, let's say 10 minutes. So then let's get back. So pipe and filter. The idea here is that we might have many different components, and then these components will pass data each other. Okay. For example, here we have one example. For example, we have microphones. Then you talk in microphones, and microphone will pass some so the data to the encoders. The encoders will process this data, and the output of the encoders is passed to the component called cancel ego that can process the data further, and then so the output data is passed to another component, and we process this data again, and then so on and so forth until you have some audio from the speakers. Okay, so the idea is that here you must think in terms of data stream, and then this data is processed by the different components. Okay, then don't think in terms of functionality. Okay, you don't have to think in terms of interfaces, but you have to think about in terms of data processing. Okay, what type of processing you can make on the data that flow between one component and the other. Then they just transform. Okay, we're talking about data transformation in this case. This data constantly fed into the pipeline. Okay, as much you talk in the microphone, and then the data flow constantly in this pipe. That's why it's called pipe and filter, because you filter the data as far as you put the data into the pipe. The nice thing of this stuff is that the process can work on concurrently. Okay, you might have different stuff. For example, here you have two different microphones putting data into the pipe, and then these are computed concurrently. That's very nice type of architectural pattern. Okay, that's very, very flexible. Okay, because allows you to just add and compose components as you need. Okay, you just pick up the component and then attach the component that you need within the pipe. Then you can extend the pipe, for example, putting a new component in the middle. You can replace one of these components with another component that provide the same transformation or a different transformation, or reorder these different components. Because I mean, that's very convenient because you don't have to stick with the API. You just provide the data. Okay, the data can be, I mean, within this arrow can be flow data in the network as a bit stream, or can be a file saved on the hard drive or whatever. Okay, we don't care. We don't have APIs here. Okay, then we don't have dependency on the APIs, but we only have a dependency of this specific data. I mean, we have this. We use this type of architecture every day. For example, when you create a file, I mean, you take a picture with your phone, then you save the picture of your phone in the hard drive, and then open this picture with a different program that allow you to manipulate the picture. For example, I don't know, an Instagram filter, then you can apply different filters, and then the output of the Instagram is published on the internet. Okay, that's that's exactly a pipe and filter process. Okay, you start by taking a picture with the smartphone, and then you can manipulate this picture in many different ways. And then you always save the output of one transformation. Then you can apply a second transformation to the previous result, and so on and so forth. And you can plug many different components as you like, and create very complex workflow. Then divide and conquer. That's every single component can be independently designed and implemented in isolation. Okay, very straightforward. Cohesion, of course, because every single component provides a specific functionality. Okay, then you have functional cohesion here. Coupling, because since you have only one input and only one output, then the coupling between the different components is very low. Okay. For example, the example with the picture, the only coupling is that the fact that they have to open a JPEG file, for example. Okay, but still, one input, one output for every single process component. The fact of having this pipeline component is very good abstraction, because you hide every internal details. Okay, you only need to know, for example, what is the input and the output. Okay, that you have to produce in order to be computed and from the next component. Reusability. A specific component can be reused in many different contexts. Just think about a component for I don't know, a filter that filter images. Okay, then we are used to put the apply filters in Instagram, but we can use filters, for example, for improving the quality of a picture for a video surveillance, for example. Okay, then the same filter can be reused in many different contexts, not only for making our picture published on Instagram. It's always possible to find reusable components. Okay, find out components that are already developed and reuse them. If you search on internet for image manipulation, you find out thousands or millions of different libraries that you can easily reuse to build your own pipeline. Another interesting design architectural pattern, which is really at the age nowadays, is the service-oriented architecture pattern, or service-oriented architecture, architectural style. Here the idea is to organize the application as a collection of services. Okay, we are now exploiting the idea of client-server architectural pattern. We are building on top of this. The idea is that we have a set of these different servers that provides functionality. And this functionality can be reused by clients that can compose this functionality and provide further functionality. For example, this web service component here is a client, because it is using services provided by web service A and the local service here and the web service B, but is also providing functionalities to another component, okay, to the web client in this case. So the idea is that we want to compose together many different servers. So in the client-server architecture, you always have one server and many different clients. Here, the idea is that we want to enlarge the set of servers that are available, and then they can be composed in this way by creating a much more complex architectures. Okay. They can be composed. It's very important, and usually these services interact each other by means of standards. Okay, XML, JSON, and in particular HTTP protocol. Okay, then so there are many different specific implementation for this pattern. There is what is called the web services that exploit XML on top of HTTP protocol or SOAP protocol. There are the RESTful web services that exploit JSON and HTTP, and so on and so forth. I mean, there are many. There are the microservices architecture, which is very famous nowadays, which is the technology exploited by Netflix, Twitter, and all the big players in the world. Okay, which is yeah, slightly different, but that's another course. Okay, at the next years. By the way, this is the general idea behind this this architectural pattern. So the idea is that we want to have many different services that are standalone, already available in the internet, and then we want to compose them in order to create a new service, okay, and provide this new service to other clients. For example, this web service can be, I don't know, the Google map. Okay, this web service can be I don't know, the I have no idea, Gmail. This local service could be the database of all the users here at the university, and then here you can combine the three in order to provide a new service. For example, given a specific person working at the university, we can visualize where is his host office, and then we can write him an email. Okay, all composed in one service that provide a set of APIs that you can exploit from a new client, for example, from the browser. Okay, then you compose three existing services to make a fourth one, which is much more complex, and then offer APIs to functionalities to the web client. Yeah, application is made of independently designed, developed, and deployed services. Okay, the idea is that services are already deployed. They exist independently of the application that you want to build on top of it. I mean, Google Maps exist. Doesn't matter if you use it within another application or as a single user. Okay, it exists. It's independent. It's up and running independently of who is using and how it's used. Cohesion, usually every single web service is structured, okay, and provide a very good functional cohesion. I mean, here, if this is Google Map, that tip will provide only functionalities about the map, okay, does not mix up the functionalities. How to implement this web service, then, but that's they can be implemented as a layered architecture or as a pipeline or whatever. As we will see, I mean, all these architectural patterns that we are discussing now can be mixed up to create a new architectural patterns. Okay, here we have three layers, but we say that the subsystem is a system that can be made of subsystem. Then this means that this layer can be implemented as a pipeline, or can be implemented as a client server, or can be implemented as a service-oriented pattern. Okay, or this three-tier pattern can be just the implementation of one of these web services. Okay, then we can mix mix up all these architectural patterns in order to create very, very complex architectures. So coupling webs, they are loosely coupled because they are just binding together components, okay, by means of communication. Okay, so we only have communication as we discussed for the client server, since we are extending the client server idea. Then also in this case, the only dependency that we have between services is in terms of network communication. But since we are using standards here, okay, then we are also solving the specific issue that we discussed about client server. Okay, that we say that, that they might be most of the time they are really application specific. But since we are using standards in the web service case, then we also bypass that problem. Then, so let's speed up a bit because I want to show you the. Next important design pattern is this message-oriented architectural pattern. Okay, they are also known as message-oriented middlewares. Okay, it's specific for communication, but it's very interesting. Okay, it's completely. This is allows you to build completely loose coupling systems, where loose coupling means in terms of space, in terms of time. Okay, that's because this message server in the middle provides a lot of nice functionalities. Okay, that's something that we use every day. Okay, we have different clients that interact each other by means of messages. Me and my mom, okay? Two different clients that interact each other by means of WhatsApp, okay? That implements the message server. They are, I mean, me and my mom use the same set of functionalities provided by the message server, which is write a message, read the message, upload the picture, make a video call, and so on and so forth. Okay, they are provided by all the message server, and then we are just using this API. So decouples the different clients in terms of space, because you can always send a message now, and I will read it tonight when I have time. Okay, then we don't need to be connected at the same time in order to interact each other. Okay, I mean, I'm talking about me and my mom, but here you have components. Okay, this can be a web server, and this can be a cart. Okay, so implementing something or a user interface that interact with the business logic by means of messages. Okay, you can send. Yeah, it's not very reactive, but you can click a button on your user interface and then let the server side to answer in 3 days. Not very appealing, I know, but that's a property. Can be appealing for many other applications. For example, yeah, a chat application. You just exploit the basic features provided by this architectural pattern. This message server in the middle provides a lot of functionalities. For example, can store the message and then forward the message when the other client is online. For example, this mom client here can be on a smartphone, then you are out of coverage, then you are not able to receive the message, then the message is stored within the message server until you get back on the network or you get back available, and then the server will provide you the message. in the case of WhatsApp. Or this can be notifications, for example. Someone make a plus on your new picture on Facebook, then this notification, okay, about you have one thumbs up is saved in the message server, and then whenever you get back into your Facebook application, then you receive a notification. Okay. I mean, not only message. I mean, messages can embed a lot of information that can be used in many different ways. And this architectural pattern is very interesting nowadays, even because allows you to implement asynchronous systems. Okay, and asynchronous systems are really appealing nowadays for many different reasons. Then senders and receivers only know the message format. I mean, you know when you chat with your mom that you have to write in your own language. Okay, that's the only things that you need to know. Okay, I use Italian because my mom doesn't speak anything else. Then I just know in order to interact with her that I have to use Italian. That's it. These messages are sent by one component, okay, which is always also known as the publisher, because it publishes the message. These messages are published through the virtual channels that are called topics. Okay. For example, in Slack, that's something that you use. You have topics. Okay, within a Slack channel, you have many different topics, and then whenever you send a message on that specific topic, all the subscriber, I mean, all the interested parties to that specific topic will receive a message. Okay? Or what happened with the mailing lists. For example, you subscribe for a mailing list of interest, and then whenever someone writes a message on the mailing list, all the subscribers for that specific mailing list receive a message. Okay? Completely asynchronous. You don't have any coupling in time and in this interaction. Well, also here a lot of good things. It provides for divide, conquer, coupling, abstraction, and so on and so forth. That's just a summary of the different architectural patterns that we discussed with respect to the design principle. There are many others. Okay, architectural patterns. We don't have time to go through them, all of them, but I guess you got the idea. Okay, now if you find a new architectural pattern, you know what to look for, and then also to understand if they are good or not with respect the different design principles that you need. Very important thing, as I mentioned before, is the fact that you can mix them up, okay, depending on the level. Okay, you can start, okay, saying, oh, I need for this first sketch, okay, of the architecture, say, okay, I want to implement a client-server application. Okay, then you might define a client and a server providing something, the client that just use the interface, and then you might refine. Okay, this okay, but what is this server? Then the server can be implemented in terms of 3 layers. Okay. And so on and so forth. Okay. I mean, you should play with them. Okay, I mean, if you decide for, yeah, for example, model view controller. Okay, I know that you know about model view controller. It's your favorite architectural pattern. I know. Last year in this class, everybody was so happy about the model view controller that when we asked to, I mean, implement an application and choose the architectural pattern, the best architectural pattern for that application, everybody choose the model view controller. Okay, then I know that you know about the model view controller. It's also an architectural pattern. It's very nice, has many properties as we discussed here, but it also has some drawbacks. You cannot always apply the model view controller. Okay, there are some type of application like I don't know, web application, e-commerce web application, where the model view controller is perfect architectural pattern. But there are some other application where model view controller is not a good choice. Okay, then you always have to, balance. Okay, the pro and cons of every single architectural pattern with respect the requirements. Okay, so the requirements are always king. I mean, the requirements drive all the development process. Okay, that's very important in software engineering. So let me stop this presentation now. I forgot to upload. What is it? Okay, so I just want to introduce you this Sonar Graph Explorer, which is the tool that we will use for evaluating our software. Okay, we discussed a lot last week about quality. We're going to discuss again about quality in the next lecture. Okay. So Sonar Graph is a commercial tool. Well, it's part of a bigger product family. Okay, we have. They provide Sonar Explorer, Architect, Developer, Build Explorer, and Build Architect. We will use the Explorer because it's open source. I mean, it's for free. We can use it without buying any license, and provides all the functionalities that we need. Okay, for evaluating our software. Okay, small project. Of course, I mean, we are dealing with small project, and then we expect that you make a massive, let's say, use of this tool during the software engineering project, because in order to keep, you remember we discussed about the quality culture. Okay, I mean, before I mean, during the development, you always have to constantly check the quality of the software that you are producing. And this tool will allow you, okay, to continuously measure the quality of the software you are developing. So it provides some functionality for analyzing the code structure, okay, in particular for visualizing the dependencies. This allows you to visualize dependencies as a graph, so that you can understand how many dependencies you have for every single class or component. You can check if there are some cycles, okay, on the dependencies. If you have cycles, it's very bad. Then this means that you have to refactor your code, because we don't want to have cycles. For example, a class A that use a class B, and then the class B use a class C, and the class C use back the class A. Okay, that's very bad design. And then in order to avoid this design, I mean, when you have many classes having some cycles, it's very easy, okay? And sometimes you have cycles that you don't know. And then by means of this tool, you can just visualize if you have cycles, and then if you have cycles, how to try to avoid these cycles. And this also provides some basic metrics, okay, that allow us to evaluate the quality of the code and the quality of the architecture. Okay. Well, something that I didn't say. This allows you to evaluate both the code in the single classes or module, but also the overall structure. Okay, and structure means architecture. Okay, of your own code. So the idea is that we want to use this tool in order to better understand, okay, how the software, well, has been produced if you are a maintainer, or has been producing if you are the developer. Okay, how you are developing your system. Are you developing in a good way or a bad way? Okay, so that will be even more clear next lecture, when we will discuss about refactoring. Okay, refactoring is very important activity during the development. Okay, and we're going to use this tool also for understanding how to refactor. Okay. So let's get started with this tool. Very few information about this. You can download the tool from this website, helltomorrow.com. You can do now if you have your laptop, or you can do it at home. I already uploaded this slide set on my Moodle. Okay, very easy. By the way, if you go to this website, you end up in this page. So first thing to do is to register, okay? Because otherwise you cannot download the tool. And then you have to fill up the form with all your data, okay? Name, last name, company. You can use Linnaeus University, it doesn't matter. Put your email address, and so on and so forth. Then once you are registered, you can log in. Okay. When you log in, you end up in this page. Okay. Then check this page. There is a link here called Sonar Graph Explorer. This is the tool that we are interested in. If you click on this link, you will be redirected on different web pages that show all the different, I mean, you have many different tabs, and then this should be highlighted by default when you click on that link. Then just scroll down the page, okay? And then at the bottom of the page, there are two links. The first is for downloading. Then when you click, you have many choices. Pick the one that fits your computer. Okay, as a Windows, a Linux, or Mac OS user, just download it, and then you install it. Okay, then installation depends on the specific computer that you have. But I mean, I tried the Mac OS. It's an installer, and it's very easy. Few clicks and the program is installed. Okay, nothing difficult. Then once you installed the program, then click on your free license here, and then a new page will open up. Okay, the page you will find the license number at the top of the page, and then at the bottom of the same page you have the instructions on how to install this license. So usually it's a copy paste. Okay, you have to open the program on your one side, and then copy the license from this page and pasting this license within the tool. I mean, the first time you open the tool, it will appear Windows asking for the license number. If you don't provide the license number, you cannot go further. Okay, that is very easy. You cannot make any mistake in that sense. So once everything is set up, you just run the tool. I mean, if you are familiar with Eclipse, you notice that there are some similarities. That's because the tool has been implemented on the base by exploiting the Eclipse framework. Okay. Then very easy. I mean, I already uploaded on my my Moodle a video tutorial, some other PDFs with tutorials. There is also a walkthrough tutorial where you can use the tool with already developed project and then click and try all the functionalities provided by the tool. Okay, that's something that you can do your own. We don't need the lecture about this. I really invite you to start playing with the tool as soon as possible, because you will use it for the assignment. Okay, that will be published on Friday. I hope. Then download the tool as soon as possible. Try to watch the video, try the tutorial. It's very easy. I mean, there are 4 functionalities to test out. I mean, we are not talking about rocket science here. Then try it. If you have problems in downloading, installing, or whatever, just let me know as soon as possible. Okay? That's it for today, and then we meet on Friday. Okay? I still don't know. I have to check this the timetable. Okay? Because it's on time edits it's 2 o'clock. But since I didn't know about this, then I have to check if. Yeah, I know. Just knew because of your colleague told me. But since I was not aware about this, and then I have other stuff to do on the afternoon, then I have to manage this stuff. Okay. By the way, I will let you know. I will put a message on my Moodle. Okay, as soon as possible.
But if you do the lecture in the morning, anyways, can you just like record and then publish? So we can watch later.